So it's been a while since I last posted, and I figured I'd give an update on what's going on with the TVC project. By the way, if you're wondering about that first clip, that was a rocket of mine I launched recently, but back to the main project. Since my last video, I took a long, hard look at what I had already made and the rest of my planned design, and I just wasn't satisfied. So I decided to completely overhaul my design and start from scratch. Just to recap, in the last video I made this flight computer, and I figured I'd just point out some of the areas I wasn't happy with in this design. To begin, we needed to address the microcontroller. The standard Arduino Nano just wasn't cutting it, and there's a few reasons for this. Mainly, it's slow compared to most other microcontrollers, but more importantly has very limited memory and storage, and has quickly run out of space to put the flight code. The second thing I wasn't happy with was with the power management. In the old design, I'm using a buck converter to take the 9-volt supply and step it down to a sluggish 5 volts to run the servos off of. Also, the old buck converter was only capable of supplying 1 amp max. However, when both servos are operating, especially at the speeds I'm planning, they're probably going to want more current than that. Additionally, I wasn't happy with the 9-volt power supply. The final thing I wanted to change was with the servos. Originally, I planned to use the servos to deploy the parachute, but I'm suspicious of this approach. Also, the servos I planned to use were pretty low quality. So let's see what I've changed. To begin, I upgraded from the standard Arduino Nano to the more capable ESP32. This is way faster. In fact, if you compare the clock speed, it's actually 15 times faster, but more importantly has way more memory and storage. Moving on to the second upgrade, I'm using some very big capacitors. The point of these is to help prevent what is known as a brownout, which is basically when you have insufficient power to run everything. They also help in igniting the ejection charge because the typical E-matches can draw over an amp of current, since I plan to switch to pyrotechnic deployment. Continuing on that point, I'm using a beefy IRLZ 44N MOSFET to switch the pyro lines, since this thing can handle up to 47 amps. Another important note is that the Arduino can't in itself switch the MOSFET, so I'm using a small optocoupler to act as a gate driver to fully turn on the MOSFET. The sensor stayed the same. I'm using a MPU 6050 for orientation, a BMP 180 to measure altitude, and the same micro SD breakout as before. Also, I upgraded the servos to these all metal gear micro servos from DF Robot. These new servos also have an analog feedback line so I can know the exact position of the servos. On top of that, I'm using a new buck converter that can supply 6 volts at up to 2.5 amps so that the servos will have more current available and be more responsive. As you can see, the buck converter is actually pretty small, so this is pretty impressive. And that about sums up all my upgrades, minus a few other small details. So let's get to building this thing. The first step is to find all the parts I need with the correct component values and just lay them all out. Here is the perf board that I'm going to build everything on, and now I'm just examining all the parts. After I get all the parts I need to figure out how to lay them all out on the board and then start connecting them together. Now this part takes forever, so here's just a few small clips of me soldering the components on. So after about a week of working on it whenever I could, here is the finished product. And I'd say it came out pretty good actually. So let me give a basic rundown of what's going on here. So here I'm showing the battery connector and switch, and I actually forgot to mention it earlier, but I upgraded from the crummy 9-volt batteries to a new LiPo battery. So I upgraded to a 3S LiPo with about 650 milliamp hours of storage, which should output about 11 volts. Moving on, the battery and pyros connect to the board through a set of terminal blocks. The input of the battery is then fed into these two large capacitors to help stabilize the voltage in the circuit. Those resistors that I pointed out form a voltage divider that I'm using to measure the voltage across the entire circuit during critical flight events. And here I'm just pointing out other critical components such as the MOSFET, the Arduino, the buzzer for state indication, the buck converter for the servos, as well as the sensors and the SD card module, as well as the test switch. I also significantly cleaned up the wiring from the last version. As you can see, the wiring here is very neat and orderly, whereas compared to the previous flight computer, I can't say the same. And here's just a few closer-up views of the previous version and the current version. So with everything explained, let me just power it up for you. If you're wondering, this is just a common XT30 connector. Great, everything seems to be in working order and lighting up well. So after this, I went ahead and tested all the functions of the board, including the servos, the pyros, the buzzer, and the SD card. Now everything was working well, except for the SD card, and that's when I said, oh. You see, micro SD cards actually work off of 3.3 volt logic, which is perfect for our ESP32. However, the breakout board I was using to interface with that micro SD card actually works off of 5 volts, which is then shifted down to the 3.3 volt logic, meaning that it wouldn't work with our current setup. So after waiting very impatiently, I got the replacement SD breakout board and now it works. In the meantime, I designed and 3D printed a mount for the flight computer using today's sponsor, Onshape. Nah, I'm just kidding, I'm not sponsored by Onshape. Okay, all jokes aside, here's the final product. And if you ask me, this is pretty cool. Just a quick 360 to see the whole thing. In the back you can actually see the battery right there. So just to quickly explain what's going on, the board is attached to this 3D printed mount so it can be attached to the inside of the rocket. The two rods are 6mm carbon fiber rods that act to give extra support to the structure, with the bonus of being lightweight and carbon fiber. Here's just a simple toggle switch to turn everything on and off. In the back again, you can see how the LiPo is mounted as part of the 3D printed structure. Then there's also a little cable pass through for the power cables. The shiny part on top is a 3/4 inch copper pipe cap that serves to hold the ejection charge. There's also a small hole on the top that didn't show that allows the E-match to pass through. And finally, for a quick demonstration, here's one of my prototype TVC mounts. This one isn't actually going to fly though. I'll go into more depth on my next video on my TVC mount design. Another point that I wanted to highlight, which I mentioned a little bit earlier, is the actual connection for the servos. I'm using 2 servos for the TVC mount, which should only require 6 pins, but I have 8 here, so what gives? As I mentioned earlier, the 2 extra lines are analog feedback lines for the servos I'm using, so I can know their exact position. So now I'm just going to hook up the servos and show you the basic idea of how this is supposed to work. Then it just gets powered on. Now, whenever I move the flight computer, the TVC mount follows. There's still a lot more to work out, especially around the software, but I'll address this in future videos. Don't worry though, as I've already gotten a head start on a lot of it. So if you've made it this far in the video, thank you so much for watching. If you're interested, in the description I have the STL files and parts list, as well as the circuit schematic. So thank you so much for watching. Please like and subscribe and stay tuned for my next upload. See you next time.